Let's go ahead and we'll look at precision and rounding using our Excel tools. So if you open up the spreadsheet and then head into floating decimal to binary annotated, so that's the second one down here. Now we're going to put in the value 0.1. Now 0.1 is going to be a value of the 0 plus the 127, so this will give us the 127 for the exponent. But what we're really interested in here is the value for the mantissa. So you can see that whenever we calculate this, we're going to have 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, and it continues like that forever. So this means that we don't have an exact value for 0.1. This would be similar to the decimal value, say 1 upon 3, which is a third, which would be given by 0.33333, and the 3 would head off to infinity. So this is the same type of number, but in a 32-bit floating point binary. It's 0.1 that we can't represent exactly. So let's close that down and we'll head into the floating point converter. Now again, if you put the value of 0.1 into the converter, you'll see here that we've got the 1, 0, 0, and then we've got the repetition 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, and that comes all the way down, but you notice there's a difference here. We've got 1, 1, 0, and there should be 0, 0, 1, 1, and then 0, 0, 1, 1. But in this instance here, it doesn't go like that. This has changed to a value of 1. So why is that changed to a value of 1? Well, it's changed because we've asked it to via our rounding. We've cut this value off here, so we've truncated it, and when we've decided to round it, so rather than truncate everything and round everything down, we're going to round half of them up and half of them down, statistically speaking, using a rounding mechanism. So in this rounding mechanism here, we can see that we would have had a 0, 0 here if it hadn't been rounded. But the gad bit is a value of 1 and the round bit is a value of 1 as well. So that means from our truth table, we would take this value of 1 and we would add it on to the least significant bit here. And that's what's happened, and that's why this 0 has changed to a 1. So let's put 0.1 in here. So you see the 0.1 being generated, but it will never get exactly to the value of 0.1. We'll get an approximation. So if we didn't do any of the rounding, this here would be our value for 0.1. But what we're going to do is add the value, the rounding on. So if we click on that, then this is the value we're going to get for 0.1. Now what I've done is I've generated an error in our approximation, so I've simply taken one value away from another. This is the value that we want and this is the value that we're getting. So in this case the error would be 1.49 times 10 to the power of minus 9. So you can see that we're going to get a number that's close to 0.1 but not exactly equal to 0.1. So now we've seen our rounding for our 0.1, let's look at our precision. If I was to change this to this value here, and let's say I continually added the values of zeros in. Okay, now you'll see all of these changing, but at a certain point our floating point number here won't change. Now let's just go down till we get to that point. So at that point there, we've actually got the same number as above. So this is all the way down to 1, 2, 3, 4, 5, 6, 7 zeros. So we get 7 zeros and then the 1. So in effect we're at this point here. Now if I was to add another 0 in, there's no change. So as far as the 32-bit floating point binary is concerned, this number here that we've written down is exactly the same as this number here. Now we know they're two different numbers, but the floating point, the single precision floating point, isn't able to represent every number, and it can only represent a subset of the number, so it's not able to represent this number. It can't represent that number, or this number. Not exactly, we can only represent them approximately. So whenever we come down to this point here, just before there's a change, and that's the change here, so I can put another 0 in. So we can only represent numbers here, in this instance here, that are going to be down to this point here. Now if we were to actually go into, say for example, C or some other languages, and we were to put in floating point numbers and do a floating point division, so we did something like 10 divided by 100, which we expect to be at 0.1, but then what we would end up with wouldn't be 0.1, you would end up with this number here, 0.1, and then there would be 1, 2, 3, 4, 5, 6, 7 zeros and a value of 1. And the reason why we're getting this is because we've only got an approximation to 0.1. We don't have an exact value. So we're only going to get the value correct to no more than about from 7 to 9 decimal places whenever we're using our 16-bit floating point binary representation. A good thing to do is to take this tool out and do the same with, say for example, the value of pi, and see what values you get for pi whenever we have it in 32-bit single precision floating point binary. So that's all for this video. Thank you for listening. I'll get you in the next video. Goodbye.